Hello, I'm Kevin Dean, a product manager from MSA Safety. Today's presentation is about protecting facilities from the hazards of ammonia gas releases. Ammonia and fertilizer production plants are subject to a number of gas-related hazards. These hazards can affect health, result in fire, or even explosion. Gases such as obviously ammonia, carbon dioxide, the depletion of oxygen due to the presence of nitrogen, as well as gases such as methane. Therefore, ammonia detection applications are often required to cover areas such as the perimeter monitoring of a plant, shipping jetties, road and rail loading areas, production process areas, pipe racks, storage tanks, and compressor rooms, pumps and valve stations. A range of sensing technologies and product configurations exist for the detection of ammonia. These include portable monitors using electrochemical cells, multi-point detection systems which use sampling systems in combination with a photoacoustic infrared technique, single-point gas detectors using electrochemical cell or catalytic bead technology, open area detection using ultrasonic techniques, and finally open path detectors using a laser-based infrared technology. For the purpose of this presentation, we're going to touch on photoacoustic, electrochemical cell, and in particular laser-based technology. First, let's have a look at multi-point leak detection using photoacoustic infrared technology. These multi-point detection systems are typically used in remote plant compressor room applications. They consist of a multi-point sequential sampling system pulling samples of atmosphere to an enclosure over distances of over 120 meters. Inside the enclosure, the sensing technology works on the principle that the ammonia molecules will vibrate in the presence of a specific wavelength of IR light. This vibration in itself generates sound, which is then picked up by a high sensitivity microphone, and that is then converted to a gas concentration. This technology therefore enables measuring ranges of 0 to 1000 ppm with a 10 ppm minimum detectable alarm threshold. Such technology is also low in maintenance, as it has no consumable sensing elements, has an auto zero capability, and has self-diagnostics for monitoring the effectiveness and performance of pumps. Here is an example of a chiller plant room using a multi-point leak detection system. As you can see, the room has a number of chillers and a refrigerant storage area. Sample points, ceiling mounted, are individually tubed back to the refrigerant monitor located on the left-hand side of the door inside the room. From the refrigerant monitor, audible and visual alarms can be activated to ensure that personnel are warned and can evacuate the area. An additional connection can be made to a remote monitor positioned outside the room, which can also be used to initiate audio and visual alarms to prevent people from entering in the event of a refrigerant gas leak. Now let's look at single point leak detectors, of which there are two main core sensing technologies being used, one being electrochemical cells and the other being catalytic bead technology. Single point ammonia leak detectors using electrochemical cell technology have been available for a number of years and typically used in outdoor process plant or compressor room applications. Recent developments have seen the ability to cable two sensing heads to a single display for the benefit of saving cost. The principle of operation is that ammonia molecules diffuse into the sensor head and react with an electrolyte. This electrolyte generates an electrical current which is proportional to gas concentration, and as a result you can achieve a measuring range of 0 to 100 ppm. However, this technology has been fraught with short sensor life as the electrolyte has been consumable, but recent advances in non-consumable electrolyte has resulted in having a life in excess of 5 years. This same advance has also improved stability in low humidity environments. When needing to change the sensor and its element, it is now possible to do that in a hazardous area without declassifying it by using what is called a safe swap technique. Single-point ammonia leak detectors using catalytic bead sensing technologies are used in similar applications. They're also available in a dual sensing head format, saving cost by only having to utilize a single display. They work on the principle that the ammonia molecules, when diffused into the sensor head, combust on the surface of an active catalytic bead. This combustion changes the resistance of that active bead and is then compared with the resistance of an inactive bead, the difference being proportional to gas concentration. But this technology is typically used for ammonia at the explosive level. Bead design can affect its performance, and larger and more robust designed elements make it suitable for areas where there is shock or vibration and can extend the life by having a larger surface area. When needing to replace the sensing element, again a safe swap capability is available, meaning you don't have to declassify a hazardous area before doing so. Now let's look at open path ammonia leak detection using laser-based infrared technology. Open path ammonia leak detectors using laser-based infrared sensing technology consist of a transmitter sending infrared light to a receiver, and for ammonia this can be done over path lengths of 5 to 120 meters. In terms of gas concentration, if you picture we had a gas cloud of ammonia 10 meters in width whose concentration was 7.5 ppm, then the output on an open path device would be 75 ppm meters. That's 10 times 7.5. This technology is probably one of the fastest for the detection of ammonia, with a response time of less than 3 seconds. The conical beam allows and compensates for either misalignment or vibration, and has a sensitivity of 0 to 200 out to 0 to 15,000 ppm meters, so it can detect small high concentration gas clouds or large low concentration gas clouds. Over the next few slides we're going to look at some different gas release scenarios and how they relate to both point and open path detection. Here's the ideal scenario. A gas release from a flange in the bottom left hand corner of the image is sending a high pressure gas release over a point detector or cutting an open path beam, both of which detect the gas release. Here the same high pressure gas release is being affected by a change in wind direction, and as a result is not being detected by the point detectors. However, the gas release is being seen by the open path device. Therefore, an open path device has a better chance of seeing a gas release in environments of changing wind direction. Here we have a different scenario, a low pressure gas release. By the time the gas has reached the point detector, it has diffused and diluted to a level that is not detectable by the point detector. However, on an open path detector, which effectively counts the number of molecules in the beam, it can be detected. So an open path gas detector is ideal for a large, low concentration gas release. Open path laser-based gas detection uses a technique called enhanced laser diode spectroscopy. The transmitter with its laser uses a ammonia filled reference cell as part of a control feedback loop to ensure that the laser remains locked on the detection wavelength. The reference cell is sealed for the life of the product and doesn't require any refilling or replacement. The infrared light from the transmitter is sent to the receiver, and due to the absorption of that infrared light by the ammonia molecules, the signal becomes distorted. At the receiver, a technique called Fourier transform, typically used by laser-based process analyzers, converts that distorted signal into its component parts, called harmonics. The pattern of harmonics is known as a harmonic fingerprint, and the amplitude of that harmonic fingerprint is proportional to gas concentration. And again, this is ammonia specific, so there are no cross interference or cross sensitivities. Laser-based open bath gas detectors are also low in maintenance. They have no consumable sensing elements. They have an auto-zeroing technique, along with being factory calibrated for life, requiring therefore no routine calibration. In terms of testing, there is a daily, automatic or on-demand end-to-end self-test facility called Simugas, negating the need for routine in-field testing. When accessing the unit, Bluetooth connectivity also reduces the time to configure and retrieve event logs for fault diagnostic purposes. So the applications typically include perimeter monitoring, NH3 storage areas, such as the picture you can see on the right of a unit perimeter monitoring an ammonia vessel, process plant areas, road and rail loading areas. So to conclude, there are a number of different ammonia sensing technologies available, of which we have discussed just 3 of them here today. One being the open path device, which has a fast speed of response of less than 3 seconds and an auto test facility. Electrochemical cells with extended life and non-consumable sensing elements, and the ability to have 2 detectors wired into 1 transmitter. And finally, a multi-point detection system using an acoustic infrared technique, reducing the cost of cabling and the number of sensors that need to be recalibrated in the field. Finally, gas detection reduces the consequences of an accidental gas release. There are a wide range of detection solutions, as we've discussed, whether that be multi-point, single point, open area and open path. An effective detecting solution requires knowledge of both the process, gas dispersion and gas detection. An effective detection protects health, plant, environment and reputation. Thank you for your time.